What's up, YouTube? Have you ever wondered in an earthquake or even high wind events what stops a building from swaying too much or even completely toppling over? Today, we're going to discuss lateral stability systems and specifically shear walls. By the end of this video, you'll understand what they are, where to place them, and how to design them in under 5 minutes. I'm going to give you some fast and loose engineering calcs that you won't find in university or in textbooks because they're intended to be sort of like engineering the fast way in the fast lane. You'll have them designed for like concept designs. They're good enough to sit your I-Strike-D exam, or even just to do a sensibility check on with the shear wall that you're designing in a concept stage, or if you're just reviewing someone else's, you just want a ballpark. I'm going to show you how to just quickly do a check in under 5 minutes that your shear walls are designed okay. So firstly, what are they? We call them shear walls. The term shear itself is just implying what the wall's doing. And when someone uses the term shear walls, that means it's acting as a part of the lateral stability system. They can obviously take vertical loads as well, but when the term shear wall is used, it is implying its function as part of the lateral stability system. It's somewhat of an ironic term because usually the shear walls, they essentially act as large cantilevers off the ground, and typically they're designed as flexural members, as you would with cantilever members. But they're not really governed by shear typically. Shear walls, they are the most common lateral stability system for buildings here in Australia. So firstly, we're going to look at where to put them if you're designing. Now, the most sensible place to place these shear walls are around, typically on high-rise buildings. You'll want some egress stairs for emergency, like fire stairs, and you'll also want a lift. So there's some voids in your floor plates, and they are the perfect place and the most common place that you will find shear walls. When the shear walls are combined into a box, people often term it a core. So they often get used as core walls as well. So when you're designing, the one thing you really want to think about, and this is like really important in terms of lateral stability design, is the layout of your shear walls. So something you want to think about is keeping your layouts quite simple and symmetrical. Now, when we say symmetrical, we're talking about aligning the center of mass with the center of stiffness. The stiffness would be governed by the layout of your shear walls. I typically want to have two walls in each direction. So that means if I got wind or earthquake coming in each direction, the load is split up between those two walls or whatever in each of those directions. And you essentially just want to have the layout of your walls symmetrical, and you don't want to put one wall in one corner and nowhere else, because you're creating torsional effects. I won't go into too much detail there because I'm just trying to do the engineering in the fast lane method here. But where you place them, you're going to put them around voids. That's the most logical and sensible place to put them, and that's when you typically find them. And if you're working with architects who want to put them in places that sort of, they're not going to be thinking about the torsional effects of where your shear walls go. So that's where us as the structural engineers, we need to step in and say, no, we need some bit of sensible thinking in terms of the layout of these shear walls. So it's something that's symmetrical. So now we know what they are. They're shear walls. They're part of the lateral stability system. They're there to resist lateral loads. Where to place them? We put them typically around voids, and they're around the lift shafts, and we want them symmetrical. And finally, we're just going to quickly design them. So I'm going to use wind as an example. If you in the I-Strike-D exam, they always give you wind speed in meters per second. It'll be the ultimate wind speed. So if you remember back at university, the Bernoulli's equation, you go 1/2 rho v squared will give you your wind pressure. Then, depending which country you're in, which building code you're using, you'll typically have to work out wind pressure coefficients. So in Australia, you have an external wall, a windward wall, and then a leeward wall. I typically combine those, and they end up being roughly around 1.2. So I call that my net pressure coefficient on the whole building. I times that by the wind pressure, and then I get I get the wind pressure on the whole building in a particular direction. That typically ends up being around 1 kPa. So if yours is significantly different to that, I think that's a bit of a red flag, and just double check. 1 kPa just somehow seems to be the magical number what our ultimate wind pressures are. Then the same way you distribute loads based on trippage areas to columns and beams, you do the same for your lateral stability system here. So in this example, you can see I've got a number of walls in a particular direction. And if that's the direction I'm looking at, I split up the load going into each of those shear walls just in that direction. And then that's how I work out the load that's going onto that wall. So now if we come and look at it in elevation, that wall, as I mentioned before, it just acts as a cantilever. So I assume that that load is, just for my concept calcs, that's a uniform load on a cantilever. So that's obviously WS squared on 2 to get our moment. And now we're going to design that shear wall like any other flexural member, where flexural concrete member, we're going to put in steel reinforcement to account for the area under tension. We'll check the compression area for compression, obviously. So that stress distribution, I go M on Z plus P on A plus M on Z will give you your linear stress profile, showing obviously the compression zone on the left-hand side and the tension zone in the right. And then, we're just sizing that area. We're checking that the steel reinforcement is adequate. I typically just choose, say, a moderate degree of crack control, which is like 0.35% of steel reinforcement in the wall. We're looking at the vertical steel reinforcement in this instance, and then I'll go and check if that satisfies the area of steel reinforcement required. And then again, go check the concrete and compression. Once that's done, there are more checks to do in detailed design for sure if you're obviously designing this, but if you're sitting the iStruct-D exam and you want to show that you understand how shear walls work and whether your design is adequate, I'd say that's probably enough right there. And again, if you just want to do a sense check of your own designs, if you're trying to check without using a computer program, this is the way I would do it. Thanks.